Imagine driving along a winding road. The car smoothly glides through curves. At certain points you shift from turning left to turning right. These transition points are like inflection points in calculus. They mark a change in the direction of curvature. Think of a smile, which is concave upward, and a frown, which is concave downward. The point where the curve changes is the inflection point. Inflection points help us analyze and interpret data. They provide insights into trends and potential turning points. In the language of mathematics, an inflection point is defined as a point on a curve where the curvature changes its sign. Curvature, in simple terms, measures how much a curve deviates from being a straight line. At an inflection point, the curve transitions from bending in one direction to bending in the opposite direction. Mathematically, this change in curvature is reflected in the second derivative of the function that describes the curve. The second derivative tells us about the rate of change of the slope of a curve. At an inflection point, the second derivative changes sign. This sign change indicates a shift from concave upward, which is a positive second derivative, to concave downward, which is a negative second derivative, or vice versa. For instance, consider the function f all x equals x cubed. Its second derivative is f double prime of x equals 6x, which is 0 at x equals 0. Since f double prime of x is negative for x less than 0 and positive for x greater than 0, we can conclude that x equals 0 is an inflection point. Calculus helps us identify inflection points systematically. Analyze the second derivative of the function. Find where the second derivative is 0 or undefined. Confirm if the second derivative changes sign. This indicates an inflection point. This knowledge is invaluable in various fields. Section 4. Types of inflection points. Not all inflection points are created equal. They can be broadly classified into two types, stationary and non-stationary. The distinction lies in the behavior of the first derivative at the inflection point. A stationary point of inflection occurs when both the first and second derivatives are 0 at that point. This means that the curve momentarily flattens out at the inflection point. The function's slope is 0 at that point, indicating a temporary pause in its increasing or decreasing trend. On the other hand, a non-stationary point of inflection occurs when the first derivative is non-zero at the inflection point. In this case, the curve continues to rise or fall as it passes through the inflection point. The function's slope is not 0 at that point, indicating a continuous change in its increasing or decreasing trend. For instance, the function f of x equals x cubed has a stationary point of inflection at x equals 0, while the function f of x equals x cubed plus x has a non-stationary point of inflection at x equals 0. Section 5. Real-world applications of inflection points. Inflection points are not just abstract mathematical concepts. They have practical applications in various fields, helping us understand and interpret real-world phenomena. In economics, inflection points are crucial in analyzing market trends. For example, an inflection point on a stock price chart could indicate a shift from a bull market with rising prices to a bear market with falling prices, or vice versa. Traders and investors use this information to make informed decisions about buying or selling stocks. In engineering, inflection points are essential in designing structures that can withstand stress and strain. For instance, engineers use inflection points to determine the optimal shape of a bridge's arch or the curve of an airplane's wing. Understanding inflection points helps ensure the structural integrity and stability of these designs. Inflection points also play a role in understanding population growth. Initially, a population may experience exponential growth. However, as resources become limited, the growth rate slows down, eventually reaching an inflection point where the growth transitions from accelerating to decelerating. Section 6. Conclusion. The significance of inflection points. Inflection points are powerful tools that allow us to delve deeper into the behavior of functions and graphs. They provide insights into the subtle changes in trends and patterns that might otherwise go unnoticed. By understanding inflection points, we gain a more nuanced understanding of the world around us. From the intricate workings of financial markets to the elegant designs of engineering marvels, inflection points are everywhere. They remind us that change is a constant and that understanding the nature of that change is essential for progress and innovation. As we continue to explore the frontiers of knowledge, inflection points will undoubtedly play a crucial role in shaping our understanding of the universe and our place within it. They serve as a reminder that even in the seemingly complex and unpredictable, there is an underlying order waiting to be discovered.